All right, picking up again from where I left off. Um, we've got this parser generating the table. Why did I write it like this? I think it's a little nicer. It's just like this. And we wanted to use the right structuring principles amongst the operators here, which it's not currently doing. So, what we're going to do is look at some methods for fixing that. And I want to look at two different issues. So, one of them is that we have different operator precedences, right? So pluses, for instance, should bind more closely to each other than equal signs, and timeses should bind more closely to each other than pluses or equal signs, right? So this, for instance, should be reading as A times B as a thing, right? Plus C equals, and then all the rest, right? But what's actually happening is it's reading as equals is the root of all of this and this, times then takes all of this information and multiplies it to the b, right? So all of this times b. We wanted to tell it that the structure of the syntax is supposed to be just the a times b, right? It's like there's supposed to be a parenthesis here and here, except that we wanted it to know that implicitly without us having to write it. So the way we can do that is from the parse function where we build operators. What we're not doing right now is we're not comparing the operators that we're parsing as we go, right? Each time we get an operator, we just stick into the chain. What's essentially going to have to change is that when we go to figure out, well, first of all, one tool we have is that we can recursively call to parse op ourselves, so that if, for instance, say we're parsing along, we do 1 plus 2 and we bind those together. That's correct. Then we bind equals to that, right? Or we're prepared to bind equals to that, and then we grab an A, right? And so then we have 1 plus 2 equals A. The problem is we can't actually bind that right-hand side thing in right away, because what we actually needed to do was say, oh, first, before we bind the right-hand side into the equals, let's double check that there isn't more that's going to accumulate underneath it. Because when this plus shows up, the equals would then say, oh, that's an operator that beats me. So I don't get the A, that operator gets the A, right? And then the A gets bound into that, and then the equals is then thinking, well, maybe I will bind the A plus B. But again, it looks ahead and finds something else, and so the A plus B, again, binds here, right? And there's a way to build this logic out of recursion right here. We also just need to say, okay, when we go to parse leaf right now, we get the next piece, right? So for instance here, we get 1 plus and we get the 2. Then we haven't decided to bind it in yet. So the first thing that's really breaking is that something new is happening right about here, because this is where we have the right-hand side, but we don't yet know for sure that in all cases the right thing to do is to bind that given the operator we're currently holding on to and the left-hand side that we already have. And the left-hand side that we already have probably has to be correct already, I think. There's no way that that's going to change, but the right-hand side is sort of potentially growing, right? So then what happens is, after you've looked at right, you're going to look ahead at the next operator and determine which one gets it from that. Man. The thing is it's a trick I've done before, but this is the part that I was worried would be most tricky to remember without going through the explicit recursive descent first. So what I'm going to do to figure it out, I'm going to sketch what this stuff looks like when you do it explicitly real quick, right? So it's kind of like I want to roll back to the more heavy-handed thing. There's like assign times plus. This loops back up to assign, and then this is like equals the operator times the operator plus the operator. This is like times plus leaf, right? There you go. There's explicit precedence. If we were parsing like this, then we'd go like assign takes in the context. It would say something similar to all this. So it'd be like node, let's call this result equals parse or expression times with the context. So this is something like this. This is something like this. Then essentially, if there is not operator, if you're not able to match the operator equals, then break, right? But if you are able to match it, then that's where you get the left equals result. You could actually simplify this and just go like exp times context, and then result equals something like join, you know, whatever, it's node operator. Let's say it's like result right, and then the equal sign or something, right? It's roughly like that. Right, and then you just drop this. Okay. And so that's how you do that one. And then you have one called times. And on the inside of the one called times, you have references to plus, and you reference the times operator instead of the assign operator. And then the pluses become leaf. The times becomes plus. The times becomes plus in this way. Right? Like that's the basic way you do it. And then the difference is so what you do is you start to think about it like this. Here, you're allowed to continue the same style of loop that you have here, right? Except that you're checking for a different operator and you're descending down this chain to the subshapes that you're allowed to check after that, right? So you're going like lower and lower down the chain in the scope of what's happening here. Now we're trying to collapse this so that all of these for loops are happening in one place and create a situation where these matching patterns are preserved through the process. So basically, this takes the leaf all the way up here, right? Because this is like assign, a calls times, calls plus, calls leaf. So it's like, okay, let's rewrite assign so that it matches this logic, but it's all in one loop. Right? That's the thought that starts it. So then you go, okay, it starts like this, if we be a little more literal. And then we do the loop. And we're saying, okay, if you have an operator plus, then you would do this concept, right? And then you'd go back around and you do it again and again, and that's how you keep doing leaf forever from a different perspective. But if you didn't do leaf, or if you didn't do plus, maybe you could also try and check for this one, right? Now, if you were here and you did not, and you did see an operator times, you would do a whole invocation of plus within that logic, right? So it's not just do this, right? It's do this, but we're trying to fold them all together so that this disappears into the loop, right? So do plus really means that you do get a leaf, and then if there is an operator, right, you do something like this, but what you're saying is I want you to check here and do a special thing, because it's like if there's a plus, we do this, and then this has to become a for loop, right? You see how as we're expanding it, there's this logic here. So I think it's something like I can't quite spot it this way either. How have I done this before? Somewhere around here, there's a way to find it. Okay, so let's start with the thing that just always works, and let's mutate it a small little way. Let me do it. Yeah, this seems like a useful approach. So we'll do A plus B plus C plus D. This will just do the right thing because they're all supposed to be left to right and equal precedence. So then the difference is if this were a times, for instance, then it's not right anymore because the times between the B and the C should be direct, and the pluses should not, between the A and the B should not, and this, I guess the plus between the A and the B should not be trumping like that, but also once these are connected like that, the rest of the plus will kind of as much. Okay, so what we have to change about the way it currently works is here you don't know anything about your precedence level yet. You get a plus, now you're at a certain precedence level. You get a B, you don't know what to do with it yet because you don't know the precedence level of this yet. So you have one thing you're holding on to, two things you're holding on to, plus an operator. So our states of information, let's try it out. So we get a leaf, we get an operator. Let's say we get a precedence level here, right? We get a precedence level, and then we get a leaf. And we don't know what to do yet in terms of how to build something with this. The next thing we get is another precedence level. If this thing here has this same precedence level as me, then I can figure out what I do with the B based on whether I'm left to right or right to left. But the rest of the cases, let's just stick with left to right for now. So if everything is left to right, then the other issue is if this is not the same as me, it's either higher or lower. If it's higher, that is, it has a higher precedence, that means I don't take the B. Instead, I recursively call and I pass down the precedence level. There it is. There it is. Okay, so what you do is you say this, what we have here, I had it before, let me back up. Yeah, this, what we have here, generalizes in the following way. Operator, context, precedence level. You pass in an integer saying which precedence level of these three you're in, right? So if there's an integer that's like 3, 2, 1 for this, for instance, then if you call this with a 3, it's like calling this. So then how does this get implemented in that language? Well, times is operator context precedence level minus 1. You check if you have an operator at this precedence level or not, and if not, you break. And again, you do operator precedence level minus 1, and right. This is a different. I've got a new name meaning for this. This is the parser function, and this used to be I've used this name a bunch of times, haven't I? This is like check operator. This is the parser for the operator. This is the node constructor now. Okay, so this is basically right, so you give a precedence level, which is basically the selector for which of these are you implementing. Now, if your precedence level is 0, you just go straight to leaf. And then what we do is we combine this with the insight about being able to do this where you keep track of what you're going to do with B in that scenario we have here. Figuring out what you're going to do with B by looking at what comes next. How does that work? You get the thing, you get the plus. Here, what it's doing that's slightly different is it's still using every level of the stack the same, right? So unless you get to, the other thing you'd have to add here is you'd go if precedence level equals 0, then this just becomes result equals exp leaf context, right? So that way, as it goes down the ladder, it eventually pops out as a leaf, and then all of this is actually in the other case. So precedence level equals 0, then you're talking about going to leaf. That way, when you put 1 in here, you're talking about plus, you go to leaf next. You put in a 2, then you talk about times, right? But then, what that means is you put in the highest precedence level first. And then it goes down, down, down until it hits 0 and finally does leaf. And then you've got your leaf and it passes back up, up, up until one of these matches, right? So it's like your stack looks like this when you do this, right? It goes highest level, your highest precedence level goes on the top of the stack, and then 4, 3, you know, your top of your stack just keeps shrinking down to the lowest precedence level. You get a leaf, right? And you parse that. Then what's next is an operator. And what you do is you go, is it an operator? You pop the 0 and you go, is it an operator at this precedence level? No. Is it an operator at this precedence level? No. Is it an operator at this precedence level? Yes. And then you consume that and once again go 2, 1, and then 0 and get the leaf and then scan back up to find the next precedence level. So the idea is, well, if the order of operations here is get a leaf and then figure out what the precedence level of the next operator is, and then parse it accordingly, why are we building out this system where we're like subtracting one down through the levels of the stack and then returning up through the stack to find a match? It's just, you arrive at this through perfectly innocent, you know, expansion of a basic grammar, and then generalizing that to like an indexed version of it, the family of functions you generated. But then it starts to be fairly clear that this is a little silly if there's a way where you can just have one layer on the stack and go, okay, parse a leaf, and then go, precedence level 3 is the operator we see. Then what would happen next is you parse another leaf, and let's see, I did back off after that. Let's say you parsed a leaf, you went back up and found yourself at operator level 3, matching that, then you tried this and this, and this parsed a leaf, and then what it's going to do is if it finds I think I had times and plus the wrong way around, right? Expressions wait, no, equals is, it's the assigns that I have in the wrong spot here. Right? Right? No, I did this wrong. This is confusing. Okay. Plus times goes below plus in the order. Times, where is my times? Yeah, this is backwards. And I think I'm going to do it like this, so that the strongest precedence is the smallest precedence. The highest precedence is the smallest number, right? Right, and then this is times and leaf, right? Okay, that makes more sense. So point of getting all of this right is to help me find the path. I want to be able to remember the path it takes you there. So for instance, with this one that I have right here, it goes, first you call parse assign. Then it goes, okay, I need to parse a plus, I need to parse a times, I need to parse a leaf. Then it finds the A, comes back with the A, and it goes, can I parse a times? Break, no, return. Can I parse a plus? Yes. So it then says again, can you parse a time? So here's the opportunity here. The skip ahead is, instead of doing these things first, you grab the leaf. The second thing you do is you say, is there an operator? If there is, you look at its precedence. And then you say, okay, this is the current precedence level we're at. The next thing we're going to do is going to be to repeat this logic we've done so far. Parse another beginning of an operator, parse another operator, and check the operator precedence that we get then, right? So we did A plus, and then we're going to do B times, and we go, hey, new operator that showed up in the second pair, right? The first pair was A plus, the second one is B times. What showed up here was a times. That's lower rank, or like that's higher precedence, right? It's got the lower like it's higher up in the chart, so it's got a lower row, but it's the stickier precedence. So it would show up right here, which means that we need to recurse and set the level at the next one down to be times. The reason we need to recurse is so that the A plus can stay in flight, right? So we got smaller, we need to go down the stack. If this had been the other way around, it goes A times B plus C, then what would happen is here, it would go grab the A, grab the times, set the precedence level, the times. Then would go grab the B, grab the plus. Oh, looks like this operator has less claim over the B than the times does. So then this folds into a new single unit, and you've got a unit and an operator again, right? And then you can look at the next one. And so at each point in time, you're either, if you look and there's not another one, then you're at the end of the chain. That's fine, you're done. If you find another whole pair, you compare the operators, and if it's an up or a down, that tells you, by an up I mean the next thing up has a higher precedence rank and therefore lower precedence, lower claim to the term. So the term goes to the other operator, the one that came first, right? Whereas if it goes down, that means the number, that is the precedence of the next operator is stronger than the precedence of the first operator. Then you recurse so that it can build up a unit that is appropriately, grouped together and then give you that whole thing, right? So that would be, in this case, you want the B times C to group together. So you say, here's a pair, here's a pair. Because of the nature of the second pair, you push onto the stack one, saying, okay, keep going, knowing that your precedence level is currently B times, and then it goes C plus, and it goes, well, plus is an up, not a down, so the C goes onto the B times, and now we have a new unit and operator. We look at the A plus versus the this thing plus, and say, okay, so this all goes together now, right? So there's the plan. I don't remember. I used to know how you could sort of get there by making the proper sort of equivalence or mutation of the spelled out version, right? Somehow you can collapse all that pattern down into this in one or two steps. But I don't remember how I have seen that before, unfortunately. Okay, so let's see what we're doing here and how far off it is. Parse op, first thing it does is get a leaf. Yes. Skip white space. Yes. Then it needs to check if it has an operator. So why don't we take a look at the token that comes up next. say, okay, if this token is an operator, then we get the operator text and the operator ID. And then precedence ID, or maybe just precedence. How do I want to do this? I get the ID, I'm gonna get the operator. I'm gonna get the precedence. And then the precedence level is the precedence order, right? So I want to build a faster lookup table from operator IDs to precedence levels before I call it quits on this. Operator precedence level accelerator. Okay. But for now, we've seen we've got an operator. We've read its precedence level. We advance our token counter. And so the thought process here, I guess, is like if there's no operator, then result is already going to do the right thing. If there is an operator, we've got that, and the precedence level that goes with it and store that information. So we've got our first leaf here, and our first operator is basically this information, right? All of this is something we computed from the operator ID. So we might rewrite it like this to separate it out properly for now, right? So really, this is the thing we are going to store later, but this information is also important, the precedence level, and we want to be able to get that quickly from an operator ID to make this better. Then consume the token for the operator. You may skip white space again. Consume the operator, skip the white space. Then we're in this position, right? We've got one I guess we'll call that left. And then this is, we grab a token. If it's a token operator, if it's an operator token, then consume the operator, skip the white space, then we take a crack at reading the right one, I guess. Read the right one. Left token. Left token. This is a little nasty. This isn't quite right. I need a clean slate. Okay. Let me think this through. I'm gonna need information for a left and right leaf in these types, a left operator ID, and a right operator ID, and a left operator precedence, and a right operator precedence. I think this is about what I need. And then just had an idea. One thing I could do to make this work a lot better is to switch this over to a token pointer. When you kick this off, you should probably give it the highest precedence possible. We'll figure that out though. This is going to be much easier now because we're just going to go to context token time whenever we want to read the current token, and token plus equals 1. You start with that, yeah, because you're beginning. Token index. E32 of token minus context tokens dot tokens. Token plus equals 1. Right, so then the idea is like should be able to do this logic a little bit more freely now. first leaf, first operator. So this is left operator ID equals, and this is where this thing and this thing happen. So why not say we just want some helping stuff for that, like parse, reading the operator. Operator, how about that? I'm going to give you the context. You're going to give me back the operator ID and the precedence level. Okay, so that I think becomes something like now if the left operator ID does not equal 0, then we're going to do more, right? So the point is the first out here is, you could just say A. Then you have a valid expression, a valid operator chain. But if you don't, just say A. Then what you do next is you give me a binary operator. And then I match that. Skip the white space of that. And now I'm here and I'm ready to do the next step. Next leaf. And next leaf is going to go into the right leaf slot. And if we get an error there, we'll go to done. And then it's going to skip white space again and get the next operator. Now there are cases here. If the right operator ID the operator ID does not equal 0. What if that doesn't really help entirely? Because what if there's an error? There's got to be an error right here. If left operator ID does not equal 0, parse error f These should include a go to done. Whenever you emit an error, then you should immediately be going to done if you weren't already. Okay. Okay, so man, I missed it. I lost the whole clipboard thing and that undo history thing at the same time. Lame. Okay. So this is if left operator ID does not equal 0, parse errorf arena context arena context, and then I give it the name error message like invalid operator, like this. So in order for this to be non-zero, it has to go in there and not hit this error. So yeah, it is the same since it's got a error. Yeah, it's got to go to done. So just it's like the same, right? Next leaf. And then you read the next operator. You put that into the right side. This similarly just needs to go if right operator ID, then the wait, operator text is nowhere to be seen now. Yeah, that doesn't work. I'm gonna need to do context token +1 position minus context token position u32 context text.string plus context token position. That's the right way to do it right now. Okay. Okay. So at this point, if you have a write operator ID, then we're in that position where, well, if you don't have a write operator ID, then that's like the case where you find this. You come up here, you find an operator, you find another leaf, and you knew you were going to find a leaf because you had an operator here that set it up, so there had to be one. But then you look for the next operator, and you get nothing. So that means the same thing as if the thing that comes next is infinitely low precedence, right? Like, it's the same as if there's an operator coming up that binds more weakly to B because you just put the A and the B together. So here we have bind right leaf into left. So this happens if the right operator ID equals 0, or if the right operator precedence is greater than the left operator precedence, or if the right operator precedence is equal to the left operator precedence and the operator precedence is like left to right, left operator is left to right. Okay. So left operator is left to right. We'll start off as false. It doesn't really matter what it starts off as. Probably do it this way though. Right to left is not right to left. So if the left operator is not right to left, how will we know if the left operator is left to right or right to left? Whenever we set the left operator ID, we'll also set this by going again into the operator and reading off right to left. No, it has to be more complicated because with the precedence, read operator is just going to need to get a little smarter. Okay, there we go. Operator, just going to give us all the info. Operator ID, precedence level, right to left. Okay, there. So we get some information about, we see if we can match the current token to an operator, and then also we match that operator to it. We look up that operator's precedence info, the level and whether that precedence level goes right to left. And so then when we do parse read operator, what we want to do is stick all of it into here. Left operator, right operator. So this will go left operator equals, and then da-da-da-da-da. And this will go right operator equals, da-da-da-da-da. Left operator dot operator ID, if right operator dot operator ID. Precedence, left operator dot precedence, left dot right operator, left operator, left operator is right to left, and it's not right to left. So if you have the case where you've got a right to left chain, let me think that through. So if you have a left to right situation, it's like this, right? Left to right is like plus A, B, C, right? So you get this sort of thing. And so the way you do it is you're holding this, you see this operator, you're holding it, you check this, you see this operator, you fuse these together, and then you've got a new left side value and operator together, and you can keep going. But if you're in the situation where you've got like A equals B equals C, then it looks like this when it's done. And so what you want to be able to do here is say, I'm going to give well, I mean, you could just build it the other way and then at the end reverse it. In place without too much trouble. But if you didn't want to do it that way, the trouble is you could think, well, okay, then if you see you're reading this from left to right and there's no parentheses, right? Well, you see A equals, then you see B equals, and you go, oh, they match, but this is right to left, so we need to recurse. So then the way that would do it, right? This would just be handled in the other case. It's just you want to do an endless amount of recursion on the right hand side of the equation. Why can't you just do this? Like, what do you do? Make a silent. What's the order you allocate and set these things up in? You'd go like because you could right now the only way I construct nodes is in the presence of the finished child nodes. I could make a change and say that what I'm going to do is keep a partially constructed operator node, right? So then I would go construct a leaf, construct the equals operator, and I know that this is the left-hand side of this equals operator, and then I would be holding this partially constructed, so it would go like this: A equals, then it would go A equals B, but not put together separately. And then it's like, okay, the next thing we see is the equal sign. So we haven't connected that in yet. And so we have a partially constructed operator. We check this and how this relates. It goes, oh, I can't take the B that you've got there. So yeah, we make a stack and we stick it on there, and we say we're coming back to this pair, but now we're continuing forward with this pair at the top. It would then read the C, and then when it sees that it's done, it would get to link that up to that, and then when it pops the stack, it will just put all the things together that are on the stack to look like this, right? Right? So it's just like do the whole stack at the end. This is just unwinding the stack at the end. Right? These steps are this connects to this, then this connects to this. Boom, boom, boom. Okay, I think I see it. So then we get new node. The node gets the left operator dot operator ID. And it gets its left and its right child right away. And then the left then the left becomes the node that we just built, and the left operator becomes the right operator. Right, so what this means is if you see something like A plus or A times B plus C, what should happen here is we make this our left leaf, or our left, make this our left operator, make this our right, make this our right operator. We compare the operators. We see that this has a precedence level higher than this, and levels are inverted so that this is stickier than this because it has a lower level, right? A lower level the number it's on lower makes it stickier. So we then say, okay, we'll build you a new node that'll represent A times B. That becomes the new left. The right operator that you're currently holding on plus becomes the new left operator. And now you can continue. And then when you continue, you'll continue where exactly? Left has been set, left operator has been set. So I guess probably right here. Right, you've got your first operator here. So from here, we'll go back to get next leaf, maybe? Although maybe this whole thing can become a big for loop. And that way, it's just the idea that if you've got a first leaf and a first operator, then we go into a loop, we get another leaf, we try to get another operator. If we didn't get the operator, or if we did but it's lower precedence, then we're going to combine them together according to the left operator and shift the whole thing in to, shift this to take over this as the left spot and shift this to take over as the left operator, and then continue back up and gather up more stuff. If let's see, so if it's going A times B plus C should go get the white space, find the operator, bind the right leaf into the left. It's going to go B plus C. So it's going to read another leaf, C, find no operator, and do this again. But what we want to do is at this point say that this is if left operator dot operator ID does not equal 0, right? So that's why we have this actually is able to live outside of this anyways. You get your first leaf, your first operator, then you begin this chain where you get another leaf and another operator, and if you couldn't get another operator, then that ends the chain because the empty operator gets shifted into the left operator space and or slot or whatever variable, and then this stops the loop, right? Now alternatively, you're looking at a pair and it's like this or something, right? So then what needs to happen is that this needs to be when you see the second equal sign, you know that you need to attach the A after this has finished. So the idea becomes you would push the left onto a stack and then shift the right to the left and keep parsing with the idea that when you are done, you recompose the stack. It's just what happens, how does there not have another, let me just see an example here. So A plus B times C triggers the same thing. So it would go A plus, and you go, okay, push that onto the stack. B times takes over. This repeats. So what happens if there's a plus D then, right? So then the times C happens. Then a plus D would mean like A plus, and the B times C happens. Because this operator is less sticky, the B times C happens, and this becomes B times C. It then has to keep checking up the stack, right? So when it goes gets So, okay, let me see this in Scratch here. A plus B times C plus D should rewrite as A plus B times C together plus D. So, right, like that. So you see, if I have a B times C here, what's happened is I compare that and I say I don't know what's going to happen. I don't think it just recurses. I mean, it goes into a stack with that, then it goes forward with this B times C, and it looks at the plus and it says, okay, we can fold these together. And then what it really has to do is look back at this and say, so the trick is, like, we want this to not keep going. A plus gets held on to. Maybe it's not on a stack. Maybe it's a little different. The B times comes up and says, I can't automatically combine. I'm bringing this down to a lower level of times. And so maybe when you recall, oh, man, I can't remember how you do it. I'm going to have to just go and look it up and then pick this back up, because I thought I would be able to sit here and figure it out. But it's like, what is it? It's eluding me. It's something like you do parse the operator. You've got a context and a precedence level. I'm sure of it. And you're saying this number can get smaller and smaller, but it can't get bigger, I think is the rule. And so if you go plus to times, you stay at the same level. I mean, you decrease your precedence level like tighter and tighter. No, I'm just not going to bother. I'm going to go and see if I can look this up. 1 minute. Okay. I've done a little bit of reading around. I think that the concept I had in mind is called precedence climbing, I think. I should be able to do it now. It's something a lot simpler than this. It's actually even simpler than this too, because what you do is you pass the node down to this is no longer really parse off. It's becoming, well, it's still just parse off, I guess. But what you do is we don't need this. So skip white space. We'll get the left operator here, like that. So we need the operator. We want to simplify this. It's bugging me that it's so fatty, but we'll make that better. Get the operator ID. If it's not 0, then let's make another helper here. should have done something like this. Just to help with making everything a little easier to read all over the place. So skip white space becomes a little less. A little less annoying. Okay, so here we get the right leaf. Skip some white space. We get the right operator. Now, this is where I was most confused. This becomes a loop, not just an if. We're going to say when we check that next operator, if and it's going to be the inverse of this. So we're going to loop on the condition that right operator does not equal 0. The precedence level is less than this precedence level, or they're the same and it's right to left. So precedence level. So if the right operator wants to be stickier than the current operator, we have another issue, which is when we look at these left operators, I'm consuming the token right away, but it's not necessarily the right thing to do. So get the next operator here. Do the conditional check here. And this happens here. Look, I'm losing track. I need to make this all smaller. Something's off. Something's just off with me not being able to think this through straight. Okay. We've already parsed the left side. This is the minimum precedence level. Or the max precedence level. Basically, we want a thing that says I can set a cap on how sticky of an operator, or how low the stickiness of the operator can get. So I can put it in this like box that's like let me look at this example here. Parsing along, let's say we've got this. We parse this, we parse this. No wait. Back it up. So we parse A plus, and now then we parse B, and we look at the times, and we compare that this is stickier than this, right? So then we call recursively with this now as the left node, and with this now as the max precedence. And so it then goes, okay, plus C, and then it goes, oh, this plus here is past the max precedence that I can put together. So then it puts all that together and returns it. and then this, which originally called for that to happen, right? So it is recursion. When you go down the table, so you get to stickier precedences, you call recursively, and you get to ones that and you lower the max precedence. And then when it hits one that goes back up in precedence, or rather loses stickiness, then it stops there and returns back up and lets a different layer in the call stack handle this that matches that plus. So it was like this, right? It's like this, except imagine if instead of filling all these out to get to the leaf and then coming back up to figure out your 3, you instead just go, okay, grab a leaf, now stick a 3 here, now grab the next leaf, and that leaf might have gone with this 3, or it might go with the thing that comes next. If the thing that comes next is a 2, then stick a 2 on the system and see what comes next. If there's another leaf, then stick them together with the 2 and then give it back to me to stick it together with 3. On the other hand, if I got this far and I've got a leaf and I've put something at precedence level 3, I found an operator of precedence level 3, and so I've got a stack. I've got a level of the stack where the max precedence level is 3, then if the next thing I find is a precedence level of 4, well, that's too big. So I take the 2 things I've got and I return them up the chain, and someone up the chain has a higher precedence level to handle that 4. That's the idea. That's the idea. Don't know how I ever found it before, but let's play with it a bit and see if I can build it now. So skip white space. We need to read an operator. This whole part sucks so much. Precedence level needs to be known. Whether it's right to left needs to be known. Yeah, it's fine for now. So we read our operator, and then we're going to say if I guess this is more like a outer for loop. We read the left operator. If the left operator has not shown up at all, then we'll break. Although parse read operator, is this even like, it's not even checking if context token kind equals token kind operator, then do all this. If we get this far and the operator ID equals 0, then I guess we can set an error that way. Maybe I need to go back and do this the slow way and recursive descent and find my way there. I don't know. I'm getting all turned around just getting error messages coming out correctly today and stuff now. Oh, I see. Okay. Okay. So this is you parse a leaf. And then you see if you can attach an operator chain to it. If the ID of the operator is 0, then you break out. I guess the way I was doing this that made sense was I was saying read operator is getting wrapped in this. So we do not have an operator token. We're done. Let's reverse this. If we have an operator token, read it. And if that is not a 0, then we've got okay. Up. I think that a part of what's confusing me is just the details about what to do with the error state. So like if this is a 0, it would be like if left operator ID equals 0, right? Then it'd be like that right there is the spot where you put in an error, and I just keep getting bogged down in it. So let me do it this way. As left operator, yes. If the left operator dot precedence level is greater than the max precedence level, then we're not touching that operator, and we break. So, okay, so if I'm reading like a plus operator after I've been at the times level, then I'm going to break and go up the stack. But if not, now I want to tie and set that left operator here at this level. still a little confused, but maybe this doesn't go in the loop. Right, maybe you read the left operator. You read the left, so I've already parsed A. I read the left operator. I begin a loop. A is not gonna have a higher precedence. A is gonna be at level, or plus is gonna be at level 2. This will be at level 3. So this will be not an increase in the level. And so because it's not an increase, it's gonna wanna keep the plus and work with it. And so then we're going to read the right leaf. We read the right leaf, and then we can try to read the left or right operator. I think. And now if the right operator when you first call this, it reads the first operator, and so it comes in A plus. I'm doing it again. I'm losing it. Let me go check this. All right. I mean, I'm kind of on it. I feel like I need to simplify out all the error handling so that I can read the code properly right now. Come back later with a mind to figure out how to make that nice. So why don't we just do it like this? So you read this if the precedence level has gone up, or if there's just no operator at all, then you break out of the loop. And then you get your right node, you get your right operator. And then what you do is you check if how Later. Okay, so A plus. If this is stickier, like it's got a lower precedence than this, we want to call this recursively. The trick is going to be something like we're passing the right-hand side B. So we parsed A and parsed plus, parsed B and put it into right. Then we saw we have a times. We can't put the B onto the plus yet. We got to figure out what's going on with the times. So we say, hey, will you parse this? But now limit, take right as this thing here we picked up here as the piece that needs to be the left-hand side of your chain. And limit your chain by this max precedence level to the right operator's precedence level. I don't want you to go any higher than that. High precedence levels, again, are less sticky in this system. So yeah, this is saying don't parse any of the things like plus or equals that have higher precedences than times. And then what comes back from that when you do that is the new value of your right-hand side. And so this is like read the operator, check the precedence, fold onto right. And so what you do is you say, okay, recursively fold right. And the check here is basically that right op precedence level is strictly stickier than the left, or they're equal and right to left. So those are the conditions under which I want to keep on recursing. So I want to take a big knot on the whole thing. And now let's work that through. This becomes that, and that separately, so that, and that. Right operator precedence is greater than or equal to this. It's like this. So if we check the right operator and there's no operator, we break out, and we don't have it yet, but there is a last thing we do. With this takes the right side and it applies, so we would do like A plus B is our right side, and it applies all the stickier stuff like B times C and gathers it up. But then it saw this plus coming, and so eventually what happens is it gets to a spot where the precedence level of the right hand side is greater than or equal to, like this, plus and plus are equal, but not left to right or right to left, right? So the logic there is we have a right operator ID. It's this is the right hand side, this is the left hand side, this is the plus we have in the left operator. Then we read the right op, we get the plus, we compare them. Now, if the operator ID is 0, we're done. If the right hand side has a precedence level greater than or equal to the precedence level, and either they're not equal or, well, this is an odd expression, I have to say. If we were to factor it out and combine this and this as an and, it would mean that this becomes greater than precedence level, or they're equal and they're not right to left. So what this means, if we don't have a right hand operator, then we're going to be done. And so that would be like if we just had a plus b, no right hand operator. And so then left becomes, and this is where we just need a new node, right? We need like a new node. Like here. So here we stick the left op.operator ID. We combine the left and the right pieces out of the operator ID finally, and this gives us our combine left and right with operator. And then it would come back around here. I mean, so say you're going along, you read a right operator, it's too big. As in, you were doing just precedence levels. So if the left operator is greater than the max precedence level, 3 times C, and then so this would go then here and go times, and then right is not right. The right operator would be greater than the left because in this spot here, because that's a plus and that's a time, so that'll be a 2 and a 1. So that'll be true. And so we'll break out of here. We'll combine the B times C here because we'll have that left operator times at this level. We'll set that and then we'll return. Then at this level, it'll get back to B times C here, and having a plus here, it will then combine that to there, and then it just needs to read the left operator again. the loop is check the operator. If there's no operator left, or if it goes beyond your max precedence level, you're done. Then check the right hand side, get this right hand piece, and check the right hand operator. If the right hand operator is an escalation of the stickiness, right? If it's stickier than you, then you recurse to it with that same precedence level. As itself, as the limit, right? It's not allowed to keep going past this. So here we would get the times would be limited to that going that far. So it would come through here. It will look at this operator. And say, no, we can't use it. Fold them in, and then look at the operator again as the left side. Okay, so one thing I should do then is say, maybe we want to do this up here, sort of, but I'll just call this the peak operator, I guess. And then we'll do peak operator. And then right here, we'll use the peak operator spot again. That way, if this breaks, then it builds a new node using the fully compiled up right hand side and the left hand side and the operator. And then the operator that it read here right before that, right, that caused it to say, hey, there's nothing else to do here on the right hand side, that now becomes the left operator, because everything to the left has been congealed together. And so now we have this ability to like peek ahead here and then reuse that information here. So that's cool. But this is not really the parse op function after all. This is like parse op recursive or something like that. Parse op then becomes a version without these. It can just go like that. Parse op recursion. Parse op. With parse op, what you do is you get your left side, and then you parse that, right? And then you don't have to talk about this here, you don't have to talk about this here. Parse op recursive. There we go. Okay. Segfault. All right. All right. So when we set this up, I now need to say that the token pointer points at tokens.tokens. That makes sense. Is the arena getting full? Yeah, okay. How is that happening? Exactly. Are we getting like stuck in an infinite loop somewhere? Token plus equals 1 happens when we get the open paren, close paren, ID num, skip white space does it. What about when we read an operator? So we peek at it, we save it, we didn't decide to end the loop, consume it. Except we don't consume the right operator because this wants to have a look at that right operator. There we go. Okay, so that's working now. So that's the A plus B times C plus D. Right? The pluses look like this because they're going left to right. Okay, so yeah, this is correctly shaped, I think. The root has this as its left side and D as its right side. And then this has plus as the root, A is the left side, B times C is the right side. This is correct, right? So we've done the precedence table thing. So we could at least wrap up here by showing, so now that you've gone that far, you can go a little farther and say, okay, at duplicative level, additive level, right, and then you go times, divide, modulo, plus, minus. Right, you can do something like that, for instance, and then and so finally, this could become like A minus B plus C, A times B plus C, A plus B divided by X plus C equals, right, there you go. Multiply, divide, modulo, plus, minus, assign, mul assign, div assign, right, and then boom. And let's see here. We've got an equality with a left-hand side of plus 1 plus 2 and a right-hand side of divided by equals. Well, that seems off. That seems like it treated it like left to right. But there at level 3, it should be saying... Well, what about a... Oh, I put the plus, so maybe it's just running backwards. Doing the minus... Well, this is right. Minus AB first, and then plus C. Yeah, that's right. B times C, yeah, that's good. It's divided by a plus between A and B, a plus equals between X and C. That's all forced by parentheses, so that's good. The D is on this equal sign here. If it's right to left, oh, well, that makes sense. That makes sense. This is correct. If it's right to left, then this isn't the root. This is the root. Yeah, okay, okay. Right to left means that the rightmost one binds first, which means the leftmost one is the root. Whereas left to right means that the rightmost one is the root. Right, like here, A minus B happens first, and then the plus C becomes the root. Yeah, yeah. Okay, so there you go. So that's the idea. I feel like this turned out super rough because I was so rusty on my precedence climbing trick. And it's still rough. So maybe next time I want to do a cleanup pass. But the idea hopefully is starting to take shape here that you can define the basics of your operators and how they set up themselves in precedence levels and how those precedence levels have certain per precedence level information attached to them, so that now that we have this up and running, later on we'll be able to expand this kind of idea with operators of other kinds. And then the other fun thing we're going to do is attach code to the operators. So that's what we're going to do next time I do this. Thanks for bearing with me while I was figuring it out today. Later, guys.